Hello students, today we will start chapter 8 Gravitation. In this, first of all, the introductory part is there, that is in early in our lives we become aware of the tendency of all material objects to be attracted towards the earth. Anything thrown up falls down towards the earth. Going uphill is lot more tiring than going downhill. Raindrops from the clouds above fall towards the earth, and there are many other such phenomena. Historically, it was the Italian physicist Galileo who recognized the fact that all bodies, irrespective of their masses, are accelerated towards the earth with a constant acceleration. It is said that he made a public demonstration of this fact. To find the truth, he certainly did experiments with bodies rolling down inclined planes and arrived at value of the acceleration due to gravity which is close to the more accurate value obtained later. A seemingly unrelated phenomena, observation of stars, planets and their motion, has been the subject attention in many countries since the earliest of time. Observations since early time recognized stars which appeared in the sky with position unchanged year after year. The more interesting object are planets, which seems to have regular motion against the background of stars. The earliest recorded model for planetary motion proposed by Ptolemy about 2000 years ago was geocentric model. In geocentric model or the geocentric theory, all celestial objects, stars, the sun and the planets all revolve around the earth, and this is called the geocentric theory and given by the Ptolemy. And the only motion that was thought to be possible for celestial object was motion in a circle. Complicated schemes of motion were put forward by Ptolemy in order to describe the observed motion of planets. The planets were described as moving in circle with center of the circles themselves moving in larger circles. Similar theories were also advanced by Indian astronomers some 400 years later. However, a more elegant model in which the sun was the center around which the planets revolve, and this is called the heliocentric theory. That is, the heliocentric theory was already mentioned by Aryabhatta in 5th century in his treatise. 1,000 years later, a Polish monk named Nicholas Copernicus from 1473 to 1543 proposed a definite model in which the planet moves in circles around a fixed central sun. His theory was discredited by church, but notable amongst its supporters was Galileo, who had to face prosecution from the state for his belief. It was around the same time as Galileo, a nobleman called Tycho Brahe, 1546 to 1601, hailing from Denmark, spent his entire lifetime recording observations of planets with the naked eye. His compiled data were analyzed later by his assistant Johannes Kepler from 1571 to 1640. He could extract from the data three elegant laws that now go by the name of Kepler's law. These laws were known to Newton and enable him to make a great scientific leap in proposing his universal law of gravitation. So now we'll move further. As we have seen in the introductory part, Kepler has given three laws. The first law is called the law of orbits because it tells us about the orbits of the planets in which they are revolving around the sun. So all planets move in elliptical orbit with the sun situated at one of foci. This was the given by the Kepler, that is called the law of orbit or the first law of Kepler's, in which what it is saying, he was saying that the shape of the orbit is elliptical, and because it is an ellipse, the two foci would be there, that is, this one is the f1 suppose and this is f2. So the two foci would be there of this ellipse, in which the one of the foci the sun is situated, and the this is the elliptical shape. Here you will see that this an ellipse traced out by a planet around the sun, and the closest point is P. You can see that the closest point from the sun is P and the furthest point is A. P is called perihelion and A is called aphelion. Here the midpoint O is situated between PA, that is midpoint. You can see that midpoint of PA, that is the center of the ellipse. This is the center of the ellipse, and half of PA, or you can say PO and AO, is called semi-major axis. PO and AO called semi-major axis. So once again, what is the law of orbit? The law of orbit is in which all the planets move in elliptical orbits where the sun is situated at one of foci. Kepler's second law, that is called law of areas. The line that joins any planet to the sun sweeps equal area in equal interval of time. Look at here, for example, it is given here that from P to Q, this is an elliptical path or the elliptical orbit of a planet, and suppose a planet is moving from P to Q here in a small time interval del t, and here the planet is moving from B to A in a small time interval, that is the same time interval in del t. So according to this law, it is stated that the area sweeps in traveling from P to Q, means this area that is shown here in the shaded part. So this area must be equal to this area according to the law of areas. Okay, so we'll prove it. This law comes from the observations that planets appear to move slower when they are further from the sun than when they are nearer. Okay, so because of this the laws came. Now we'll prove it. Just to prove it, we'll see here as we have taken from P to Q. This is from P to Q, a small displacement is there, that is you can consider del S. Okay, and in short time interval del T. So the area sweeps, suppose we are considering here as del A. So we'll see here the area. Let area PSQ, which we have seen, that is equal to del A in a small time interval del T. Okay, so as we know that the area here, this can be considered as a triangle. Look at here, this can be considered as a triangle, and in which the PQ can be considered here as a base, or any of this, either you can take PS or SQ can be taken as altitude, because this is a very large distance compared to PQ. The PS and SQ are very large distance compared to PQ, so almost altitude we can consider here. So just apply the triangle, the area of the triangle, that is half into base into height. So the base we will consider here as del S, and height we will consider here as R. Okay, or so we'll see here, this is the area, that is del A, which is half into base into height, and as I told you, we can take this area PSQ. This is area PSQ is equal to half, and base we are taking here as PQ, and height as PS. Okay, so this is PQ and this is PS. Now we'll see the area del PSQ, which is del A here, is equal to half. PQ is the displacement as we have taken here, that is del S, and multiply with PS is the radius here, that is PS is the radius. Okay, now what we'll do, we'll just divide this equation with time, the small time interval, or we can replace del S, that is the displacement here. So the displacement can be replaced by the velocity into time. So we'll write here, that is velocity into time. Okay, so a small this velocity into time here. So this way also we can do, or either we'll just divide here with this quantity del T here. Okay, so then also we'll find the same thing. So del A is, here we'll write del A, which is equal to area del PSQ is now equal to half. Replace del S with del V and multiply by del T, and this is R here. Now the del A here, this del T will take this side. So del A del T is equal to what? It is half del V into R. Okay, del V into R. Now we'll see that this is del A upon del T. What we'll do, just multiply and divide with the mass of the planet, that is m del V into R upon, this is m here. Okay, so this will give us what? This is del A upon del T is equal to half. M del V is P, linear momentum, that is mv. We know that this is equal to P, the linear momentum. Okay, so we'll replace m del V with P, and that will be del P, that means small linear in momentum. Okay, now you will see that this is R or m here. Okay, now we'll see that this is del A del T, and we know that the P into R, the linear momentum and the radius, will give us the angular velocity, angular momentum. Okay, so we know that the L, which is equal to Rp in magnitude. Okay, so we'll replace here half L upon m. That means what comes here, that is del A upon del T, which is also called the aerial velocity. This is also called the aerial velocity. Okay, so this came here L upon 2m. Now look at here, as we know that in the planet which revolve around the sun, there is no external torque is working. It is moving in the, means whatever rotation it is taking, the planet is, so no external torque is working. When no external torque is working, that means the external torque is zero. In such situation, we know that the angular momentum, this L, which is what? Which is angular momentum. This is constant quantity. This is constant quantity. And even you know that the mass of the planet m, which is the mass of the planet, this is also a constant quantity. Okay, so overall what we find here, we find here that L upon 2m is a constant quantity. L upon 2m is a constant quantity. That means the aerial velocity del A upon del T, which is the aerial velocity, that will be constant. Okay, so it will be constant here. That means what it is? If it is constant, simply what we can say, the area, this area. Okay, because when del A upon del T, a very small quantity, so if the del t tends to 0, if you can say simply. So in such situation, this del A upon del t you can write as dA upon dt, and in that situation the quantity A will be what? That will be constant. A is also a constant quantity. Okay, so A is a constant quantity. Area with respect to time is constant here. Okay, so A is constant here. That means the area is constant for the time interval t. So whatever del t time interval means whatever area swept by the planet in time interval del t, that would be constant. That means simply you can say the area, that is PSQ, and the area that is given by ASB here. Okay, as you can see in the figure, that is area here given by the PSQ and ASB, both must be equal, and this is called the law of areas. Kepler's third law, that is called law of periods. According to this, the square of time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. That means if t is the time period of revolution of a planet around the elliptical around the sun, means around the sun in a elliptical path, so t square, the square of the time period, is directly proportional to the radius, or you can say the semi-major axis of the ellipse, the cube of the semi-major axis of the ellipse. That means t square is directly proportional to r cube, where t is the time period and r is the semi-major axis. Now we will define gravitation. The force of attraction between everybody or any two bodies of universe is called gravitation. That means in every object applying a force on any other object in the universe, so this attractive force is called the gravitation force or the gravitation. Okay, now the Newton has given the gravitation law, that is called the Newton's law of gravitation. According to it, the everybody in this universe attracts every other body with a force which is directly proportional to the product of their masses and is inversely proportional to the square of distance between them. So this is the Newton's law of gravitation. According to it, just now the law says that the force of attraction, that is called the gravitation, between the two bodies. Suppose we have taken here the two bodies of mass m1 and m2, and the distance between them is r. So the gravitation force F is directly proportional to the product of the masses, that is m1 m2, and that is this is equation 1, suppose. And according to the law, the gravitation force between these two objects is inversely proportional of the square of the distance between them, that is 1 upon r square. So this is second equation. Now if we just combine these two equations, combining the two equations, that is equation 1 and equation 2, so F is directly proportional to m1 m2 upon r square. Now if we remove the proportional sign, one constant we will apply here, that is called a proportionality constant, and given here g, that is m1 m2 upon r square. So F is equal to capital G m1 m2 upon r square. This is called the Newton's law of gravitation, that the gravitation force, the formula for the gravitation force between the two bodies is given by G m1 m2 upon r square, where G is a proportionality constant called the universal gravitation constant, and m1 m2 the product of the product of the masses of two bodies, and r is the distance between them. Now we'll define universal gravitation constant. To define it, we know that the formula for the gravitational force is given by F is equal to G m1 m2 upon r square between two bodies of masses m1 and m2 which kept r distance apart. Okay. Now if we just apply the condition here, let the two bodies are having the same mass, that is 1 unit, or you can say unit mass. Okay, and even the distance between them is also suppose 1 unit. So in such situation, if we just apply the formula here, we'll find that F equal to G, the product of two masses will be 1, and the distance between them will be 1, so square of that distance is also 1. That means what here? It is F equal to G. It is F equal to G in this situation. So now we are in condition of defining the universal gravitation constant, and it is defined as the universal gravitation constant is equal to the force of attraction acting between the bodies each of unit mass whose centers are placed unit distance apart. So once again, the definition of universal gravitation constant is that universal gravitation constant is equal to force of attraction acting between two bodies each of unit mass and whose centers are placed unit distance apart. Now we'll see that the SI unit of universal gravitation constant. To find out it, we'll just see here that F, just leaving G here, rest of the quantity will transfer this side. So G is given by here, that is Fr square upon m1 m2. The SI unit of force is Newton, and the SI unit of the distance is meter, so it is meter square. The SI unit of masses are kilogram, so this is kilogram. That means it is Newton meter square per kilogram square. So what we can say, the SI unit of G, or universal gravitation constant, is Newton meter square per kilogram square. Now we'll find out the dimension formula of universal gravitation constant. Already we have seen the dimension formula, how it is calculated in the second chapter. So once again we'll see that G is given here Fr square upon m1 m2. So G here, the dimension formula of force is mlt minus 2. Dimension formula of radius is L is square L square. Mass is given here m into m here. That means G is equal to m would be cancelled. This m will go up, so it is m minus 1 L cube T minus 2. So the dimension formula, this is dimension formula of G, is given here m minus 1 L cube T minus 2. Now important characteristic of gravitational force. According to Newton's law of gravitation, the gravitational force of attraction between two given bodies is independent of nature of intervening medium. That means if the two bodies are kept here of masses m1 and m2, the distance between them is r. So whether these two bodies are kept inside the water or in the air medium, whatever it is, so if the masses are unchanged and the distance between them is unchanged, in that situation there would be no change in the force of attraction, the gravitational force of attraction. That means the force of attraction or the gravitational force is not depending on the nature of the intervening medium where these two bodies are kept. Okay. Second is independent of presence or absence of other bodies. Suppose you bring any other body in between these two bodies, so the gravitation force between these two body will not change in presence of any other body. Okay. Third is independent of nature and size of the bodies. Whatever size, whether it is a spherical, means the size of body is large, or the small, if the mass will not change, the distance between them will not change, there would be no change in the force of attraction or the gravitational force of attraction between the two bodies. It depends on the product of mass and the square of the distance between them. Okay, so if these two physical quantity will not change, so the force will remain constant. There would be no effect in the size or shape or the nature of the body. Okay. Then the gravitational force of attraction between two given bodies form action and reaction pair. Action and reaction pair, that means if one body applied force on the another body, suppose FAB is the force applied by body B on A, and FB is the force applied by body A on B. So these two forces will be equal in magnitude but opposite in direction, and hence they obey the Newton's third law of motion. That means they will make the action reaction pair and they will just obey the Newton's third law of motion. Next, the fifth point is the gravitational force are central force as they act along the line joining the centers of the two bodies. That means the gravitation force between these two bodies are called central force because they are acting towards the center of each other. That means if it is applying the force on this, so directly it will apply the force towards the center of the first body, and the first body will also apply the force on the towards the center of the second body, and so that these two forces are working between the center of the line joining the center of the two bodies, and that's why they call that's why this force is called means the central force. Okay. Now the next point, the gravitational force are conservative in nature. Conservative in nature, that means whatever path you will choose here, but you will find that all the time the gravitational force will be means it do not depends on the path, it simply depends on the initial and the final point. Means because it is working between the two bodies and the line joining the centers of two bodies, so by whatever path you will check it, that will be means constant always, and that's why it is called conservative in nature.